Hi everyone, welcome back to SL Academy. In this session, we are going to learn how to implement a stack using Java's DQ. You will understand what a StackDeque is, how it works internally, and we will walk line by line through a working Java program. By the end, you will know exactly why modern Java prefers array DQ instead of the old stack class and how to apply in it real projects. Learning goals. Here's what we will cover. Recap what a stack is and how to LIFO works. Explore the DQ data structure and its two-ended flexibilities. And learn how to restricting DQ to one end make it behave exactly like a stack. And walk through the complete Java implementations and analyze performance and see real-world usages. Let's start with the basics. A stack follows the last in first out rule. Think of stacking places. The last one you put down is the first one you pick up. The core methods are push, add to the top, pop, remove the top, peek, look at the top without removing it. Stack appears everywhere in the function called tracking, undo, redo, operations, expressions, evaluations, and algorithms like DFS or backtracking. DQ primer. Now meet the DQ, short for double-ended queue. Unlike a normal queue, it let you insert or remove at the both ended, the front and the back. Main methods: add first, add last to insert, remove first and remove last to delete, peek first and peek last to inspect elements. This dual nature is powerful, and here's the key idea. If we operate only one end, the DQ behaves exactly like a stack, like LIFO. The insight is the foundation of our StackDeque. Why DQ is instead of java.util.stack. Before coding, it's see why array DQ replace stack. Array DQ is fast, no synchronization overhead. It's cache friendly and uses modern design. The legacy stack class is synchronized and slower. So the single-threaded or local stacks always choose array DQ. Introducing StackDeque. To build a stack from a DQ, we simply chooses one end as the top. This implementation, the right end will act as a top. So our mapping are push, add last, pop, remove last, peek, peek last. Everything we do happen on that one end, leaving us true LIFO behavior. Everything we do happen on that one end, giving us true LIFO behavior. Here we can see how a StackDeque in Java works using a push-pull operations. In first step, we start with a empty stack. We push a number 9 using s.push9. Now, the element 9 is at the top of the stack. Then, step number 2. We push another number 7 using s.push7. new element is always added to the top of the stack. So now 7 is above 9. Third step, we push on one more element 11 with s.push11. Now the top of the stack is 11 followed by 7 and then 9 at the bottom. Finally, step 4. We can use pop method. This removes a top element which is 11 from the stack. After popping, 7 become a new element. So, in summary, a StackDeque follows the LIFO rule, last in first out, and the last element we pushed away, the first one is to be removed. So here we have Java implementation of generic stack built using ArrayDQ. Inside the class StackDeque, we first create a dq called dq, and it acts as a storage for our stack elements. The push method adds a new element to the top of the stack using addLast. It also checks null values to avoid errors. And the pop method removes and returns the last element added. Just like a real stack, the one of the top goes out first. And if the stack is empty, it throws an exception. The peek method. Simply look at the top element without removing it. Then we have size, isEmpty, and clear methods. These are help methods to check how many items are in the stack, whether it empty or remove all items. So overall, this code is simple, usable, and reusable, and safe stack implementation to using Java ArrayDQ. And you can use this code by description under the video. Demo using StackDeque in action. Here we test our stack with integers. We create a new StackDeque integer and push 3 numbers 9, 7 and 11. So after each push, first stack has 9, then 9, 7, then 9, 7, 11. Next, when we call pop, it removes the top element that is 11. Then peek shows 7, the new top element. Finally, size returns 2 because we still have 2 elements left, 9 and 7. So this demo clearly shows how to stack works. Last in, first out. That means the last pushed element and always the first to come out. LIFO, last in first. Performance and complexity. All main operations are O1 on average. Push, pop and peek take constant time thanks to the array-based resizing of ArrayDQ. Space grows linearly with elements O(n). That's why this structure is efficient and the wide used in Java applications. Real-world applications. You will encounter stacks everywhere. Browser history, undo, redo, syntax parsing. Those are real-world applications. Then browser history. So 2 stacks back and forward pages. Undo, redo. 1 stack it for undo and redo actions. Syntax parsing. Compiler checks matching parentheses with the stack. DFS and backtracking algorithms use stacks to explore search paths. Conclusion. To sum up, a dq can add remove from both ends, but if we operate just one end, we get a perfect stack dq. Using array dq gives us modern, fast and clear LIFO behavior. That's how we implement a stack using Java's dq, elegant and efficient to ready for the real world. Thank you for watching.